Unit 6 is thermochemistry. So all reactions involve breaking bonds and forming bonds. It is the difference between the energies of each that determines if the reaction is endothermic or exothermic, which helps determine if it's spontaneous. All reactions obey two laws: the law of conservation of mass, which we saw in Chapter 3 with balancing and stoichiometry, and the law of conservation of energy. So energy cannot be created or destroyed, however, it can change forms. There are 5 different types of energy, and energy is just the capacity to do work or to produce heat. So kinetic energy is produced by a moving object. Radiant energy is solar energy, so it comes from the sun. Thermal energy is associated with the random motion of atoms and molecules and can be calculated from temperature. Chemical energy is stored within the structural units of the chemical substances, the bonds. In the reaction, energy is released, stored, or converted to other forms of energy. And then potential energy is available by virtue of the object's position. So, for example, if you're standing at sea level, you have one type of potential energy. If you walk up the mountain, the force of gravity becomes stronger, so you have more potential energy. The law of conservation of energy, again, the total quantity of energy in the universe is assumed to be constant, so you cannot create energy or destroy energy, but you can move between the different types of energy. Energy changes in a chemical reaction. We first need to know what the difference is between heat and temperature. So heat is the transfer of thermal energy between two bodies that are in different temperatures. Remember that heat goes from the hot thing to the cold thing. Temperature is the average of the kinetic energy of those molecules. Thermochemistry, which is what we're doing in this unit, is a study of the heat changes in a chemical reaction. So besides knowing those types of definitions, we also need to know what a system and surroundings are. System is the specific part of the universe that is of interest to us. So for example, if we're reacting HCl and NaOH, the beaker that has HCl in it, and we're going to add NaOH to it, that's the system. The surroundings is everything else in the universe: the atmospheric pressure, the classroom temperature, everything beyond that particular reaction. We can do reactions in 3 different systems: open, closed, or isolated. An open system is when you can have an exchange of mass and energy, and it's usually in the form of heat with the surroundings. So if you look at the first bottle there, that's an open system. It's open to the atmosphere, so we can lose some mass through water vapor, and we can lose heat through the container. Now if you put a stopper on the top, then it's a closed system, so it only allows heat to transfer, but not the mass. An isolated system means that you can't transfer either mass or energy. So if you look at the third bottle, it's insulated, so it's going to keep the heat in, and then it's capped, so it's not going to let any mass out. So when we look at a calorimeter, we're trying to make an isolated system. An exothermic process is any process that gives off heat. It transforms the thermal energy, or transfers the thermal energy to the surroundings. So there's the picture of the Hindenburg explosion. So you have H2 plus O2. You're doing the combustion of hydrogen gas, and that's going to form water vapor. It's a very exothermic reaction, which is why the Hindenburg exploded. An endothermic process, the heat has to be supplied to the systems by the surrounding. So mercury oxide's decomposition is endothermic. We actually have to give the mercury oxide some energy in order for it to decompose. So if you look at the diagram on the upper right, you can see that the products were higher than the reactants. The reactants were higher than the products for an exothermic, but it's reverse for endothermic. The reactants are lower than the products. Alright, so an introduction to thermodynamics. It's the scientific study of the interconvention of heat and other kinds of energy. It provides useful guidelines for understanding the energetic and directions of processes. A state of system are values that are relevant microscopic properties, so like composition of the atoms, the energy that they have, the temperature, the pressure, the volume, things that you're used to talking about. State functions are those properties that are determined by the state of the system regardless of how the condition was achieved. So if we talk about changing pressure, when we look at a gas and we change the pressure, we don't really care how the pressure is changed. For example, did the volume increase and then decrease to make the pressure change, or did the temperature go up and then come back to constant? That part doesn't matter. The pathway is independent of the change. The first law of thermodynamics says that energy can be converted from one form to another, but it cannot be created or destroyed. So if U is the internal energy, then the final minus the initial equals the change. So the internal energy of our products minus that of the reactants would give us the internal energy of the reaction. If we look at the system and the surroundings, if we add the change in energy of the system and the change of ending of surroundings, it should equal 0. So whatever happens to the system, the opposite's happening to the surrounding. So energy lost by one system must be gained by another. So in our calorimeter, when the metal loses heat, the water has to gain that heat because the heat has to go somewhere. Now it can be transferred in a different form. So we could be talking about a chemical energy being transformed into thermal energy, but the value, the magnitude has to be the same. So in chemistry, we're interested in the energy changes associated with the system, not the surroundings. So we need a more useful form of the first law. So we say the internal energy is equal to Q plus W, where Q is heat and W is work. The subscript system is dropped from the U just for simplicity. So the change in the internal energy is a sum of heat exchanged between the system and the surroundings and the work done on or by the system. If heat is lost, then it's endothermic and Q is positive. If heat is if heat is gained, absorbed, then Q is positive because it's endothermic. If heat is lost, then Q is negative and it's exothermic. Now, if work is done on the system, W is positive. If work is done by the system, then work is negative. All right, so what is work? Work is force times distance. So work has a broader meaning that includes mechanical, electrical, and surface. Electrical work we'll really talk about when we get into electrochemistry later on in the book. Mechanical work and surface work is kind of what we're going to look at. Mechanical work, if you think about gases, I think it's the easiest to use or to think about. Pressure, we know, is force per area. So if we force the plunger down, we're doing work on the system. Now if we let the plunger go up, our volume is going to increase. Well, that difference then times the pressure is what work is. So you have work equals force times distance, and we know that pressure is force per area, so we can say work is force per area times distance. So work equals my pressure times my change in volume. So we can figure out work by looking at the difference in pressure and volume. Now when you do that, you get this liter ATM, but because we're talking about energy, we would want joules. So you do need to remember this conversion. It is not in your reference tables. You need to remember 1 liter ATM is equal to 101.3 joules. Alright, so for example, a gas expands from 264 milliliters to 971 milliliters. So my change in volume, final minus initial, is 707 milliliters. Calculate the work done in joules by the gas if it expands against a vacuum. So a vacuum just means that the pressure is equal to 0. So work would equal negative P delta V. So work would equal negative 0 times 707 milliliters Alright, so that would give you 0 for your work. If it expands against the constant pressure of 4 atm, work equals negative P delta V. Now I'm going to go ahead, negative 4 atm. I'm going to go ahead and change my milliliters to liters, so 0.707 liters. And our work would be negative 0.2828 liter atm, but the question asks for it to be in joules. Well, I know 1 liter atm is 101.3 joules. So that gives me a value of negative 286.5 joules. And because it's negative, I know that work is being done on the system, or by the system. Because it's negative, work is being done by the system on the surroundings. That should say agas expands and does PV work on the surroundings equal to 279 joules. At the same time, it absorbs 216 joules of heat from the surroundings. What is the change in energy of the system? So we know that the change in the energy is equal to Q plus W. Now it's absorbing that amount of energy, so my Q value would be a positive 260 joules, plus the system does work on the surroundings, so that's a negative 279 joules. So the change in energy then is a negative 63 joules.